All right, good afternoon. How you guys doing? Do you appreciate the brief little break from at least from this class last week? Yeah, I'm feeling much better. Thank you. It's kind of about a week of a bad sore throat. I just didn't feel like I could lecture on Thursday, so hopefully today will be fine. I think so, and got a couple cough drops in case. Okay, how'd you feel about the exam? Okay, I should have come a little more prepared to ask about it. So I see some middling, some like nope, don't talk about it. Some maybe okay. Uh, give a small subtle hand gesture if you felt like it was too long. Okay. Um, challenging, but somewhere near right, near near okay. Raise your hand really high if you felt like it was the easiest exam you've ever taken. Just kidding. Kind of. Okay, nobody. All right. So I haven't been able to grade them yet, but so next week we have Mardi Gras, um, and I don't think I'll have them done by Thursday this week. So probably a week from Thursday, uh, should have your exams and homeworks back to you. Um, but I was talking to one of you at some point in the past week, and really, this is my first time teaching this course at the undergraduate level. So I I understand that I may make mistakes. In fact, I did make a couple. Thankfully, they weren't huge ones. You know, in class I clarified, okay, use 25 Celsius for this problem, and then that set a lot of you up to think about the last problem, which was like at standard temperature pressure, but it didn't give any specific temperature. And so I had, I was kind of reminding a few of you, well, it's a standard temperature. It's STP, right? So there was a couple small things like that, but hopefully with the clarifications, hopefully it turned out okay. All right. So all that to say, if it turns out it was just a brutally difficult exam, I'll account for that and make sure that it's not unfairly harsh. And I give partial credit when I grade, so you'll see all that next week. Okay, so before the exam, we had just kind of wrapped up talking about the elements or the core pillars of putting together a larger equation, multiple equations together, so that we could basically get one equation with one unknown is kind of the target. So we're doing combinations of, we have multiple unknowns and multiple equations, putting them together such that we end up being able to solve, 2x equals 5, what is x? Kind of a deal, right? Algebraically. So this is kind of where we left off. If we consider some generic acid HA, we know there's 4 species there, and we have these different equations we can derive from that. So there would be H plus and OH minus because we have got water, A minus and HA. So those are the stuff in solution. And you can imagine if we had some other solvent not water, this all changes a bit, right? So if you had some pure liquid of some other kind, it's going to be a different world in some ways. But we're in water, always going to be in water for this class. And we're going to go ahead and assume that this activity coefficient that you now know how to work with is going to be 1. So we can just treat all the concentrations as they are. And then our 4 equations would be the equilibrium for water, the equilibrium for this acid, so Kw and Ka, and then we have a mass balance for total concentration of the acid. Sometimes people write it as C. A lot of times we've been using the A total, and that'll be the combination of HA and A minus is the total of all species that contain A in it is kind of what we're summing there. And last, we could do an electroneutrality equation. And we would set that up like this. So we're not going to touch on proton balance equations yet. We're just going to stick with these 4 until we really introduce and talk about that, the critical point, or excuse me, the equivalence points. But we'll get there in this next few lectures. and discuss the relevance of a proton balance equation. But for now, you've seen all these four, you've worked with these four, and we're going to take a look at how to bring those forward into a solution to figure out, okay, we have some amount of acid, it's like A total, let's say, what's our pH? Or what's the ratio, what's the alpha fraction kind of thing, right? Okay, so let's take this example of HA and move forward to derive one equation that we can use to solve with. And then we'll bring out Excel and kind of take a look at doing it graphically and take a look at using Excel's solver function. Okay, so we have, well, what we want is some linear starting point. So we talked about this once already. It's kind of nice to start with our electroneutrality equation because it's in a linear form to begin with, meaning there's no divisions or anything like that. So that's probably a good starting point, and we'll work from there, because if we started with one of the K equations, we've got a fraction to begin with, right? Now we could use algebra and deal with that, but we'll just start here. Okay, so then from our mass balance equation, we can take a look at what can we add to, or what can we substitute into our electroneutrality equation to reduce the number of unknowns, right? If possible, we just want one unknown, maybe pH, right? Maybe H+. So if we aim to get H+ as a function of x, y, z, where x, y, z are all known, that's fantastic. So from our mass balance equation, we can get an equation for A- to substitute into there. Okay, so I'm going to clean this up just a little bit for you. So with the target of substituting that part in, we can use the alpha fractions. And if you remember, we define the alpha fractions starting with alpha 0 as the fraction that is the fraction of the acid that has lost exactly 0 protons in total. And A1, the alpha 1, then is the fraction that has lost 1 proton. So in this case, this would be HA, and alpha 1 would be fraction of A-. You remember that? And we can derive that then as, for A-, that would be A- divided by HA plus A-. And we went further and simplified that, and then combined the, well, it's all written out right here for you, right? We combined the equilibrium constant for Ka to simplify it further. So this, we could divide everything by A- and get HA over A- plus 1, and ultimately go from there to get that. Okay, so that's the alpha 1 here, and alpha 1 times the total amount of A gives us the total amount of A- at that, under those conditions, right, at that given pH. So that's why A- equals alpha 1 times A total. So if we know something about A total, and we can solve for the alpha given the equilibrium constant and a pH, then we know things. You know, we are able to put A- in terms of several knowns, because presumably we can know something about the Ka. So if we write, let's say the knowns would be something like, we probably know A total, we probably know Ka, Kw, and the unknowns then would be things like HA, A minus H plus, which is probably what we are going to use as what we solve for. And OH minus. Now, if we know H plus, then we know OH minus. So that's another, but that's because we have an equation for that. Okay, so these are the different pieces going into this. So I'm going to come back to the writing here, the text that's already on the screen. So we get that from the mass balance. We then substitute that in, right? So we have H plus is equal to A minus, which is now alpha 1 times A total, plus OH minus. Now, because we have the equilibrium with water, we know that Kw is equal to H plus times OH minus divided by essentially 1 because it's water. That gives us the relationship here, and we know Kw. Okay? So let me just, I'll rewrite this. So we'll say okay, so we can substitute in place of OH minus, now we have the Kw divided by H plus. So what we've done so far is we put the A minus in terms of the alpha fraction and A total, which are, the A total is in the camp of the knowns. The alpha fraction will be known if we know the pH. So the alpha fraction is essentially the same as pH, assuming we know the Ka. So it's all sort of feeding back into, can we put it in terms of H plus and knowns? Okay. All right. So now we have this equation, H plus equals alpha 1 times A total plus Kw over H plus. Continuing from there, which kind of have that most of that up here already, we can say that, well, if that's our equivalence, then we could set the whole thing to 0 by just subtracting both sides by H plus, right? So if we take the left-hand side minus the right-hand side, or the right-hand side minus the left-hand side, or whatever, however we want to do it, that's going to set it to 0, right? So we can say 0 is equal to H plus minus all that, right? So minus alpha 1 A total minus OH, except instead of the OH we had already substituted, right, the Kw divided by H plus. Okay, and that's all written out here more clearly, so don't worry too much about my notes there. So we can end up getting this equation here. Right, and what you see here is they've expanded out the alpha. So alpha 1 is that chunk, right? Is this making sense? Putting the equations together? Okay, so the reason this is all helpful is because now this is a little more manageable as something to solve. So if this was an algebra problem, you might be looking at that and thinking to yourself, if I have to solve for H plus, that's going to be a little ugly, right? How do we get those things out of the denominator? You probably can do it, but it's not going to be fun, right? So moments like those, it's nice to have some sort of computational help. So we'll get there in a moment. But you can see that has become an algebra problem because we know Ka, At, and Kw, right? So this thing can be solved for H plus, right? And we're going to take a close look at a couple ways of doing just that. Okay, to kind of sum it up a little bit, we now have the one equation with one unknown. And so one thing you could do, and you could even do this in your calculator. Everybody have a calculator? Maybe we ought to do this. So, or a computer. If you have your computer with you, just go ahead and get Excel out because we're about to be using Excel. You can get that set up, and I'll get the value of Ka for you. We're going to use 10 to the minus fifth for Ka. A total is going to be 10 to the minus fourth. And of course, Kw, we should know, is 10 to the minus 14. So given that, try putting in 3 or 4 guesses at the pH and see if you can get closer to 0, right? So the pH range is from 0 to 14. And just by guessing, see if you can get approximately there. And if you get quick at it with your calculator, you can go back and say, okay, I'm just going to edit the input and try again, right? Or in Excel, you get it all punched in. You can just change it. So see if you can get that set up to at least make a couple guesses as to what value of H plus gets you to 0. That's the challenge, right? Is to put the left side of that equation in. How close to 0 are you? Are you far from it? Try a new pH. Or H plus, really. In fact, if you get an answer, you can share it with the class. Just tell me what pH you used. And we'll say, we'll just make a quick little table. Who's got a low pH value that you've already tried? Anybody? Not yet. Okay. Let me know if you get an answer for one.
The concentration of H plus would be roughly in between 10 to the minus 16 and 10 to the minus
So
18.
what you ought to do is you ought to select one pH and then convert that to H plus. So we're going to make a little thing with pHs. Maybe select an even pH if you haven't chosen one yet. But that's going to range from about 1 molar down to 10 to the minus 14th, because that's 10 to the 0 is 1, and 10 to the minus 14 is 10 to the minus 14, right? So you could either select a pH or just say 10 to the minus some number. And it's going to be some random like value. It might be negative, it might be positive. It's not going to be, none of you will get exactly 0 on this because it's not on an even pH value. So it's not going to be obvious if you did it wrong. That's what I'm saying. Anybody get an answer yet for even just one value? For what pH? Okay. No, that's fine. I'm just going to edit a little bit as I go. So you said 0.99? Okay.
9 times 10 to the negative 5 for 4.
Okay, so 4, 9 times 10 to the negative 5. Great. So we can see right there that pH 4 is a lot closer to it than pH 1. Anybody have something higher than that? We're trying to get it close to 0, basically, is what we're looking for. Anybody have a higher pH?
So the idea is that we're translating the pH into the H plus concentration to try and make the equation equal to 0.
Yeah, so what I'm asking you to do is just try one H value, right, on the pH scale. So H plus, we'll say 10 to the minus 4, somebody already did that, right? You just put that in for H plus and see what value comes out. And then once we're gonna take that and make guesses until we get it as close as we can to 0. So maybe one thing we should do is try to get, since we're already close to 0 with 4, maybe let's do 3, 5, and 6. Now let's do 1. So somebody try those. Are you getting stuck on putting this in or something, or like what? So for those of you who have not spoken up yet, are you getting values and you're just not sure, or like what? You're just not getting it into your calculator, or what? Okay, putting it in wrong. That's fair. That's fair. And I mean that's part of why I'm having us just like, hey, let's try this, right? Anything else other than calculator issues? I mean, okay. So anybody have a value for 3? So 10 to the minus 3 for the H plus concentration.
I got
0.00099. Okay. How about pH 5? Anybody? 0.000 times 10 to the minus what? 5. Okay. How about 6? 10 to the negative 5, you said? Okay, great. So let's pause here and take a look. And it's kind of cheating because I already know a little bit. But as we go up in pH from 1 to 3 and from 3 to 4, we are clearly decreasing in like closing in on 0. We're getting closer to 0. Now, 4 to 5, we have to stop and take a think about this. And then we realize, okay, they're both 10 to the minus 5th. So we can just kind of ignore all the decimal places for a moment and say, all right, is 9 or is negative 4 closer to 0? And negative 4 is closer to 0, right? Okay, so then we can move on and say pH 5 is the closest so far. 6, now it's negative 9. Again, this is times 10 to the minus 5th. That is also further away from 0 than the previous one. So based on this, we would guess that this answer is somewhere near pH 5, right? So this is exactly what we're going to do in Excel, but Excel is going to do it for us a little faster, and we can do it in a couple ways graphically and with a solver function. So I hope this was helpful to just get a feel for how to do the root solving type of thing, right? Find the root, so to speak. Okay, does that make sense, kind of the process of what we just did? Even if the calculator was annoying? All right. Okay, so we're going to take a look at Excel with those same parameters that we were just doing, and as a bunch of text from one of our books, if you wanted to be a little more elaborate or like see what the book had to say about it. I think it's going to be saying approximately everything we're about to say, and then it has this nice little figure that we're going to look at our own version of that in Excel. So let me pull that up. Okay. So I made a Excel sheet here, generic acid HA, and if we take a look at these are the same values that we used in that problem just now. So this is the same problem, right? The same setup with the left-hand side minus right-hand side equals 0. And we've got this function here. We're going to call it f of h plus. So is equal to the left-hand side minus the right-hand side. And this is what we're going to try to drive to 0. And it's just got exactly the text that we were just working with, right? It's got the h plus minus, or excuse me, yeah, minus the alpha 1 times a total. A little bigger. Time divided by, or excuse me, minus kw divided by h plus. Okay, so to approach this, we know we need this as a function of h plus. So that's kind of like back in math, we did f of x, and so x is our x-axis, obviously. So what we're going to do is, since it's f of h plus, but we also like to work with the pH scale, we're going to set up a bunch of pH steps and then calculate the h plus at each of those steps. Okay, that's going to be a convenient way to work because, as we were mentioning earlier, the h plus concentration can be very small. Like it can go all the way down to 10 to the minus 14th on the pH scale. So we don't want to step through 14 orders of magnitude by every 0.1 or something like that, right? Or tenth of a step. We want to just go ahead and step on our log scale and just calculate the h plus accordingly. So I went ahead and did it stepwise by every 0.1. Of course, we could do more refined than that, but this is already going to take us 140 or so rows for that. And of course, our pH next to it is calculated each time as this is 10 to the minus the pH value, right? So that's all just kind of set up there. And now we want to calculate alpha 1. So alpha 1, of course, we talked about earlier, is going to be what we use to get a minus. And we derived that alpha 1 is this Ka divided by H plus Ka. Or we could say this is 1 over H plus divided by Ka. Because you can see you could divide the top and the bottom of this portion by Ka, and it simplifies a little. So regardless, it doesn't really matter too much how we calculate it as long as we calculate it. So in each cell here, what I'm doing is I'm calling up to the Ka to find our alpha fraction at that pH. I'm going to say it's Ka, and if you notice, I've got the dollar signs here. That tells Excel this is not going to move anywhere. Don't shift this anywhere. Keep it exactly here. Whenever I copy this into new rows or new columns, it's going to just stick there. And you can freeze the columns or the rows or both. And if you wanted a cool little shortcut, you press F4 and it toggles through adding those. Right now it's freezing the rows but not the columns. Now it's freezing the columns, not the rows. Now it's not freezing anything, and now it's freezing both. You can do it manually too, but that's F4 on a PC. Okay, so we've got this equation then. It's just solving for the alpha 1, like we've talked about. So then we solve that throughout, and if we stop and think about it a moment, alpha 1 is the fraction that is is A minus, right? So it's the one that has lost a proton, meaning if there's a lot of acid around, it's probably trying to add protons to it. So when we have a very acidic condition, like pH 0, it's a very small number. That meets our expectations. That's good. And then if we can just do a quick little check, we should have mostly all the unprotonated version at very high pHs because it's trying to pull that proton away. There's so much OH minus around that would like to just become a water molecule and combine with the H that was hanging on the HA. So almost all of our acid is in the form of A minus up at that high pH range. Okay, so that checks out. Looks like it's working just fine. Now we have the last column, and we can plot this as the F of H plus, right? So this is essentially what I'm going to do is write in to this column this equation that I had all of you try in your calculators, right? So this is just my way of automating or putting through what you guys just worked on to get me a few numbers all into here. So we can take a look, and the equation again is calling to the A total, the KW, the alpha fraction, and if you notice, the alpha fraction has already taken the Ka, so I'm not actually calling the Ka directly, but it's kind of caught up in that, in the alpha. Okay, so when we do that, if I have it in there correctly, which I think I do, that will calculate the value of that left-hand side of the equation that should be 0 when we find the right pH at a given pH. So we're just kind of going to guess through the whole range of pH. So we start at is 0.999999, and we can actually come through and double check. Somebody tried it at pH of 1, and I think you got 0.0999. So we can check our guesses here. I think I didn't hear you correctly. I think there was a 0.0, right? Okay. Okay, so that's looking good. And we can see we're getting closer and closer to 0 as we scroll. pH 3, we had 3 zeros and then 9999. So pH 3, yep, that's exactly what we had. I didn't carry it quite far enough, but you know, you get the picture. Add another. pH 4, 9.09 times 10 to the minus 5th. That's looking good. pH 5, that should be, yep, -4 times 10 to the minus 5th. And pH 6, -8.99 times 10 to the minus 5th. So all of that's checking out really well with the calculations you made. And if we go further, we can see we're getting more and more negative all the way down to -1 at pH 14. Okay, so let's find the 0, because we know it's near pH 5. And now we can take a look just at the raw data if we want to. This is the, you know, maybe not the easiest way to do it, but we can do it this way. And what do we see? Well, there's a 10 to the minus 6. There's a couple of them right here. So these two are getting us to our lowest spot, and then we can pick the one that's closest to 0 and say that's according to our precision, which is 0.1 pH. We could increase that. Maybe we could even locally increase that and get a little more precision that way. Just adding a few more decimal places for the range between and around those guys. But at any rate, what we see is 4.6. That gives us a value of negative 3.3 times 10 to the minus 6, where the 4.5 is 7.6 times 10 to the minus 6. So our answer then would be this guy. Right, that one, of all of these values, we just found this guy's the closest to 0. Does that make sense? Okay. Now, the other thing we can do is simply graph it. Now, the graph I have so far is maybe not the most convenient. Well, let me back up one step. We'll come back to the graphing. The other thing we might be interested in is describing the rest of the system. So when we say we're solving a system, well, we just found the pH. That will let us get values for all the other things, all the other species in the system. Now that we've kind of conquered it, hopefully we should be able to calculate everything else, right? So we're going to say at pH, oops, 4.6 is what we found, right? So therefore, what we can say is the OH minus should be, this will be Kw divided by that 10 to the minus 4.6, right? So I'm just going to grab 10 Kw, divide by 10 to the minus pH that we found, which is 4.6. Okay, so now we have an OH value. And now we have A minus and HA. So what we can do is say this is going to be equal to, we'll start with A minus because that'll be a little easier. We're going to say that's going to be equal to the A total times the alpha fraction that we found, which that's the third column here, at the minimum. And that'll give us a value. Theoretically, that should be less than our A total, right? So if this was larger than our A total, we've done something wrong. But our A total was 1 times 10 to the minus 4th. Okay? Now, from our mass balance, we could solve for the alpha 0 if we wanted to. I think the easiest way to do this part would be to say, well, if the total is 10 to the minus 4, then HA is going to be the total minus A minus, right? So we can say this will be A total minus A minus. Okay, there we go. Right, so now, given the total amount of acid, we had to guess some pHs to find it. But once we did, we could then describe everything else in the solution. Of course, we also had to know the dissociation constant for the acid. All right, does that make sense? How do you feel about that?
Would you also be able to? You can also just subtract the OH concentration for the hydronium concentration from the OH, and you could also receive the A minus, right? From the original.
What you could do is you could take pH 14 and subtract the pH value 4.6. So 10 to the minus that number that is your answer is your OH minus concentration. Is that what you're saying?
Or just that once you have the OH concentration, that you can find the A minus using the electroneutrality.
Oh, true. Yeah. So you could call back to the electroneutrality equation. That's a good point. Yeah. Very good point. Yeah, I like that. Okay, so the other aspect here is we can graph this. And at the moment, the graph maybe is useful. What I've done is I went ahead and put the alpha fraction on there. Alpha 1. We could also put alpha 2, and it's kind of going to do the inverse sort of thing. And I also graphed the f of h+. And to be honest, the alpha fraction doesn't really need to be there, but since we calculated it, I went ahead and put it on there. If we just focus on this orange line, that's the f of h+, that's the one where we want to figure out where it's going to 0. As we notice, it stays near 0 for a very long time. So we probably need to adjust to the graph, which we can certainly do. So that's not a big problem, but I was just kind of pointing out what it looks like across the whole pH scale. Right? So if we wanted to use this in a way that's going to give us a bit of a better answer, we probably need to shrink this down to about 10 to the minus 5 as the positive, like 1 times 10 to the minus 5 and negative 1 times 10 to the minus 5. Or we'll do 1 times 10 to the minus 4. Did I do that? No, I accidentally hit auto, sorry. No. I did that. Oh, I did it just backwards, right? So minimum needs to be negative. And maximum. There we go. Okay, so now we have a situation where we can actually draw a line across 0 and see where it crosses. Somewhere like that. And it says the point that it's crossing at is 4.6. So that's pretty handy. And in fact, I think we could probably change the graph type itself and give us, instead of a smoothed line, what would be better? Let's see. It would be a scatter plot. There we go. Yeah, so now we see the closest point there between 4.5 and 4.6, like we said. Okay, but you could see, and we could even zoom in, take the pH between 4 and 5, and then, make a better, even more exact guess. And that's kind of what the that thing on the slides is showing. Okay, does this all make sense? Any questions or issues? All right, so you're ready to do it for homework, right? With the more complicated system? Okay, maybe. We'll come back to this, though. Okay. So that's kind of what this graph up here is showing, and that's kind of what the text here is documenting a little more closely as it passes through 0, and you could zoom in on it and get a little more precision on your data points. And it turns out the answer that they came up with is the pH should be 4.57. So between 4.5 and 4.6, and closer to 4.6. Okay? So, pretty good. All right, from there, and we already did this, we could take a look at the OH minus, the HA, and the A minus concentrations. And so these are the values that hopefully we just solved in Excel. And as we discussed, you can do this in a couple of ways. We have all 4 of these equations. There's a very good note that we could use the electron neutrality. We just go back to that equation. It's pretty simple. We could use the mass balance, or we could even just calculate the alpha fractions like they're doing. So one way or the other, these numbers were 3.7 times 10 to the minus 10. So pretty close. Now they use 4.57. We're using 4.6. So our numbers are a little bit off. 7.15 times 10 to the minus 5th and close to 3 times 10 to the minus 5th. And we see that they're 7.3 and 2.7. Okay, so not too bad. Okay, so now if we use a solver, here's a whole bunch of text if you want it. What I'm going to point out, it's actually pretty useful. It's going to describe a lot of what we are about to do. The automated solvers do exactly what we were just working on. They make a guess, and they make a second guess and see, is that closer or further? Okay, if closer, we keep going in that direction until it's further, and then we stop and backpedal, right? That's what the solver is going to do. And if I gave you, let's say that same problem on an exam, your best bet would be to guess something that's like middle low pH and then middle high pH, and then see the difference, and then go from there. Try one in between. Just check kind of stepwise, right? To try to minimize the number of calculations. I'm not going to do that. Maybe I'll have you do a little bit of that kind of stuff, but not too crazy. For a solver system, we just want it to be able to get us good precision relatively quickly. And as we saw, it didn't take long for Excel to do that, or it would not have done. We were the slow part in preparing the Excel sheet, right? Okay, so a couple notes here in this text. I'm just going to say that as it's approaching 0, the solver system itself has some value in mind of what's an appropriate amount of distance from 0. And if that appropriate distance was 0.1, that's not going to work for us very well. Because if we look back at our graph, there was a lot of that graph that was within 0.1 of 0. Right, so we need to make sure that it's not 0.1, it's 0.000001 or something. Right, so this is just saying there's a caveat here that convergence criteria, we have to be a little bit careful. We need it to be a really small thing. So 0.1 is too large. Of an error. So really, most of this text is coming here just to say the easy thing to do is just to take that answer that we were getting for the f of h plus and multiply it by 1,000,000. And then whatever error we had, however far away from 0 we were, it's now 1,000,000 times bigger, which puts us to the point where 0.1 might be reasonable. I don't know if 0.1 is really the number Excel uses or whatever, but I'm just letting you know that's going to be a way we can increase our precision pretty easily. So that's this whole first part. It talks about MATLAB and Solver for Excel. And the second point is, we actually already talked about this a little bit. We should change pH and not H+, because we're going through 14 orders of magnitude. If we were to step change in H+, like incrementally, that's tons of calculations. We don't really need to. pH is on a log scale for a reason, and if we need to scan that whole log scale, let's use the log scale to scan it. Okay, so that's, in a nutshell, that's what all this is talking about, and you've got the text there if you want to take a closer look. Of course, we have to calculate with H+, but we cannot we have to do that conversion from pH to H+, is what I'm saying here. Okay, so let's just say search by H+, not H, pH by not H+. Okay, so let's take a look at what that looks like in Excel. So I have a second sheet of this thing, and I basically have the same stuff here, and even the same rows, and we have different pHs, or we could guess different pHs here. I'm just going to set that to 0 for a moment. So this is literally just the same stuff I had in the other column, but I just moved the f of H+ equation down a bit. Okay, so we had, in the other sheet, we had the f of H+ here, whole column of it. Right now, I'm just taking the very first row of it, right? So everything else is the same. This is the equation to get H+, right, from pH. This is our alpha 1 equation. And that's kind of how we have it. All right, so now the f of h plus equation, I put it here. It's the same exact equation. It's going to call to the knowns and then call to the h plus. And here's where we were solving for a bunch of them given different pHs, right? That was the last slide, or last sheet. This time, we're going to tell Excel to make a guess at the pH until we get this number to 0. So Excel's going to guess to get this to 0. Guess at this to get this to 0. And I can probably write that over here. So we're going to tell Excel guess pH to make f of h plus approximately equal to 0. Okay, and you notice I have it twice. I'm multiplying it by 1,000,000 the second time, so we can just see how much better precision we might get that. Okay, so how do we do this? Well, we're going to use the solver thing. So if you go to data in your Excel sheet, you might not have it, so you might have to add it. I think we already talked about this once, so just real quickly, you would have to go to your file, into options, you go to add-ins, go to Excel add-ins, oops, yeah, and make sure you have solver add-in added. Okay, once you do that, it should show up here. And if you have trouble with that, Google could probably help, or YouTube or something. I'm also happy to help, but I think that'll be the quicker and easier way for you. Okay, so then what we're going to do is doesn't really matter where we have our cursor yet. We're going to click the solver button. It's going to bring us up this prompt, and we have to set an objective. The objective is kind of the target to say this equation that, if you recall, we put in an equation in that spot. We said this is equal to xy divided by 3 times b c d, right? Whatever that is, we're going to set that objective. I'm going to go ahead and set it to the one without multiplying it by 1,000,000 yet. And we're going to set it to a value of 0. So that's the target. The objective of the solver is to get this cell to 0. And right now it has whatever, it has the calculation as if pH is 0, which is 0.9999. So that's the objective. That's the value we're targeting. And we're going to get there by changing the value of this cell. And here we can put our pH. Okay? So we're going to change pH. Well, solver is going to change pH and try a bunch of different numbers. I didn't even tell it only goes up to 14. I just told it, good luck, right? I think we can set some extra stuff, extra constraints. So we could probably say something like, this guy is always less than or equal to 14, or put in a cell that says 14. So I could constrain it, and maybe that helps. Maybe I know something else about the system, or maybe have an entirely different thing. Okay, I think I added one. Yeah, so now we have that constraint. The pH has to be less than or equal to 14. Okay, no problem. So that's something just to let you know that could be added if you did have a weird system, or if it was giving you a negative pH value for some weird reason. Yeah, maybe set that greater than or equal to 0. Okay, but that shouldn't affect anything whether it's there or not. So I'll just leave it in for now. Maybe it speeds things up if you were able to narrow it. Now, there's some fancy stuff here that maybe we use and know something about these. I sure don't. but there's a GRG nonlinear, there's a simplex LP, there's a evolutionary method. I don't know. I'm just going to use the default and it's going to work. That's what I know. So if you need to get into some fancy stats, there might be some more info about that. And it even gives us a little description. Solving problems that are smooth, nonlinear, select and it tells us, right? Select this other one for linear problems and select the evolutionary for solver problems that are non-smooth. Okay, ours is pretty smooth, right? It was, no weird stuff. Okay, and I'm going to tell it to solve, and it pops up this thing on my screen. Bring it over here. It says, okay, solver found a solution. All constraints and originality conditions are satisfied. It's asking me if I want to keep the solver solution. Sure. I could probably return some extra stuff, maybe make some sort of report. I'm just going to say okay and see what it gave me. And it gave me a value here, negative 6.96 times 10 to the minus 7, and the pH value was 4.74, and so on. And one thing I'm going to do real quick is I'm just going to copy that and paste it here, just so we can compare when we solve it with a times a million to see how different that might have been. Now, it feels to me like that's pretty close. That's still the 4.57 that the book arrived at. But we can do the exact same thing. It'll be very quick now that I've already talked about it all. And we can simply try setting a different objective, right? We want to set the times 10 to the, to the 6, 1. Okay, and by the way, if you take a look at the equation, all I've done was actually set it equal to the equation above it times a million, right? So Excel will actually track that and say, oh, okay, well, when we change pH, this is changing by some amount because that one is multiplied by a million. So that works just fine. Okay, so now we have a solution, and we see it is a little different. It came up with 4.568 instead of 4.574 or 575. So a little bit different, presumably a little bit more accurate. We are a little closer to 0. And I guess maybe that's a meaningful amount. A little more accuracy doesn't hurt, and so just multiplying that by a million is a good call. Okay, does that make sense? So you can use this in a lot of problems. You'd be surprised. There's a lot of systems out there that can make use of Excel Solver. So I'm gonna try to give you a meaningful reason to use it within your homework this semester. Hopefully that's a good resource. Now, MATLAB can also do it. So I think I have a couple more slides, but we might just pull up MATLAB and see if we can at least find the function together and see if we can begin setting up that same thing here. Okay, so here's the formal prompt for all that we just did. We could also make an Excel sheet that looks like this. This is an example from our textbook. I also have a separate spreadsheet just like that. So, basically everything I just talked about, but put in this form. That portion of the assignment didn't do the graphical thing. That was kind of something I've added this time. So I looked back through my notes this morning and I was like, oh, I already had an Excel sheet. Oh well, now I've got two. Okay, so let's take a look at MATLAB and see if we can figure out a bit about MATLAB Solver. It's going to take a moment to open. Any questions on Excel while we've got it here? No. Yeah.
The other day I accidentally, instead of like on the first column, I accidentally typed the equation into like the second column, and I couldn't like fill down because it's there a way I can just like copy that equation to go above, or do I just have to redo it?
Yes, I think so. So what you're saying is you had some value here you wanted to copy. Well, let's say
Or some equation.
some equation, right? So you said, I'm just making up something, right? So this, you have an equation that says this is equal to this times 33. So, and maybe this changes, but you accidentally started here, right? Okay, so, and you wanted to fill up. I think you can, well, one thing you can always do is you can just copy. So copy like that and then paste, and it does it. It should do it. What just happened? Oh yeah, sorry. Let me do this again. So if you did equals this guy times 33, then, and now you wanted to shift it up, you can copy and paste because it's going to just shift the cell reference. Now, sometimes it might be a little more convenient to simply delete a row. So let's say you could just delete that altogether, that shifts it up, or you could delete, let's say you realized, oh shoot, I also needed 0 there. You could, and I don't want the calculations to change, you could insert a cell and shift everything down, shift cells down. That'll move everything. Likewise, you can delete and shift cells a certain direction. You could even delete, let's say, a few cells, and it'll again ask you, okay, where are we shifting? Are we shifting the cells to the left? In this case, I want to shift them upwards, so they all go up 1. So a few options for you there. The Control D or fill down or fill to the right, I don't think those go left or up. And maybe they would, but usually it's okay just to copy and paste and delete or insert like that. Okay. Oop. All right. So now we've got Excel, MATLAB. Let me get my screen out of the way. Okay. So let's see how fast we can figure out solver. Oops. Always start with help solve. Hey, it's something. Okay. So solve. Oops, that's QUBO, quadratic unconstrained binary optimization problem. Searches for a solution. Okay, so we can write solve something. Now, I'm not sure if we are using a quadratic binary, unconstrained binary optimization, but that might actually be the technical term for it. So let's see if we can do solve x plus 3 equals 0. What's that? Oh, thanks. And I might have to, okay. So instead of equaling 0, maybe I need to add a constraint. So I'm going to start with x equals 10, and now try this. Okay. So let's say result equals. Okay. I think this is probably not, solve is probably not the exact right. Let's see if I have any solver. Not found. Okay. So at this point, I would go and search the internet and say, what do we have? And I'll just do this for 5 minutes with you and then let you go. And this is probably what I read earlier thinking about this. So solve function should give us something, but let's take a look at MATLAB's actual answer instead of that. Okay, so to solve for a variable other than x, specify, so maybe it's just because I was doing it wrong. Okay, so let's make this bigger for all of us. So if equation, so we have an equation, we solve equation, comma, x solves that for x. Okay, so let's try that. Instead of,
I think it said you need like a double.
Yeah, double equal sign, or you could let them in a single apostrophe.
so something like that.
And maybe get rid of the x and the comma.
Okay, so they're using this as solution equals solve something. So I'm going to say equation equals x plus 3. Maybe that's, yeah, actually I probably need to use that double equals there. That's probably, okay, so I'm going to say equals 0. Okay. And then I'm going to say solution equals solve x. Oh, how did they do that? Solve the equation EQN, comma x. Okay, still no. Okay. Well, not to bore you too much more with my troubleshooting, but hopefully a couple minutes of it at least gave you an appreciation for, I'll be doing the same thing as you when I approach a new problem in MATLAB. I haven't touched it in a while. I have a lot more experience with you than in MATLAB, but I also can't just show up and figure it out instantly necessarily, right? But this is the process that you kind of go through. It's like, oh, did that work? No? Okay, did that work? And I'm doing this before I even get to a script, right? So a lot of times you can play in the prompt and just see, hey, is this working? Is this, no? Okay. And normally you're not in front of a classroom either. So that's to your benefit. All right, so I'll let you go with that and we'll do some more next time.